At the very front of logical headway is the European Board for Atomic Research, CERN, eminent for its momentous commitments to molecule physical science. As of late, the undeniably popular Molecule Physical Science Lab has uncovered a very interesting finding from its Huge Hadron Collider that could totally change how we might interpret the universe. Researchers accept these bizarre discoveries could reveal the presence of outsider life in an equal reality. This earth-shattering thought has started fervor and serious conversation among specialists. Could this exceptional disclosure reshape how we might interpret the universe? Furthermore, whenever confirmed, what significant experiences will this revelation offer into the nature of reality itself? Go along with us as we dive into the as-of-late distributed discoveries, exploring how CERN researchers are ending their silence on this chilling new revelation that has the potential to change all that we know. The European Committee for Atomic Research, otherwise called CERN, has been popular for its thrill-seeking tests since its origin during the 1950s. It has been at the center of attention a few times, both for good and for ill, but its tests have stirred worry about the potential development of black holes, cracks in our reality, and numerous other dangers. One of CERN's most popular and dubious accomplishments was the development of the Large Hadron Collider, LHC. The LHC is the world's largest atom smasher, starting operations on September 10, 2008, and it remains the latest expansion to CERN's accelerator complex, crossing over 27 kilometers of superconducting magnets and a progression of speeding-up devices. The CERN supercollider cost more than $4.5 billion. Many would contend that this money was carefully spent since the LHC has brought about some of the most significant disclosures of the last few years, such as the discovery of the Higgs boson and many other previously obscure particles. This tremendous machine is capable of speeding various particles around the circle until they reach close to light speed and complete more than 11,000 laps per second. The LHC does this with a succession of extremely powerful electromagnets that produce a magnetic field inside the accelerator that is nearly 100,000 times more prominent than the field that surrounds the Earth. Some have expressed worry about the effect of creating such strong magnetic fields on nearby hardware as well as its impact on the Earth's own field. Once these particles arrive at their maximum speed, multiple particles heading down contradicting paths are compelled to meet in a brutal crash, delivering enormous energy and a variety of particles. When particles impact, a flood of particles escapes out this way and that, with most of them enduring only fractions of a second before decaying. Changing the source of particles permits specialists to uncover new particles in this whirlwind. Extremely sensitive detectors are installed around the crash sites to record all the data from each collision. This measure of data mounts up rapidly and requires a huge amount of time and work to go through each year. The LHC's tests produce more than 15 petabytes of raw data from these impacts, which need to be purposefully filtered to extract the information the scientists need. In 2017, the LHC achieved a significant milestone by permanently storing more than 200 petabytes of data in its tape libraries. To put this amount of data in perspective, 1 petabyte is equivalent to around 250,000 movies. But what exactly are they searching for in all of this data? They identified something unusual happening with a particular kind of particle called a beauty quark. Quarks are the major building blocks of matter and exist in different flavors, as characterized by physicists. Some of these quark flavors are truly unstable, decaying into different particles in the blink of an eye. The beauty quark, with a normal life expectancy of 1 in 1.2 trillionth of a second, became the focal point of attention due to a particular variation. Its decay pattern contrasted from what researchers anticipated in light of the Standard Model. According to their expectations, when a beauty quark decays, it will be affected by the weak force and transform into a bunch of lighter particles known as leptons, either an electron or a muon, with the Standard Model predicting a 50-50 chance for the two particles. However, the LHC data revealed that these quarks decayed into muons only 30% of the time, while decaying into electrons 70% of the time. This anomaly could exist if a previously unknown kind of particle is involved in the process. This has led some scholars to think that some new type of physics might be at work. A new force-carrying particle would suggest pristine physical science that could expand the Standard Model and answer many perplexing questions. The possibility of new physics challenges the Standard Model hypothesis, which provides our best understanding of how the odd universe of particles acts. The Standard Model is a scientific framework that definitively explains every aspect of our insight into the actual world's building components. The surprising thing is that, despite this serious level of precision, physicists are very much aware that this model still needs to be completed. The Standard Model only describes three major forces: electromagnetic force, strong force, and weak force. There is currently no description of gravity or an explanation for dark matter, the universe's common type of issue. During late preliminaries, specialists found an error in the data they were assessing that diverged from what is known in the Standard Model. Although it isn't uncommon to find results outside this framework given the volume of data produced by the LHC, this time something piqued researchers' interest, and they saw the need to explore more to determine this new event. What might this brand new force be? To explain this surprising revelation, the scientists proposed the existence of another essential particle, which they refer to as Z', a force-carrying particle. Despite the fact that this particle is the best bet, it is very weak, as there have been no indications of it until recently. The specialists believe it would interact differently with electrons and muons, but the degree of its interactions with Standard Model particles remains obscure for now. If researchers find new force-carrying particles, it would be a 10-year hotly anticipated breakthrough in physics. That's what physicists hope. If this discovery is confirmed, it will serve to unravel well-established principles. Secrets of the universe make sense of old issues, such as what dark matter is and the Higgs boson's role. In the current day, some researchers believe that this unseen power could help satisfy one of physical science's most significant objectives over the last century, bringing together the essential forces of existence. According to Elon Musk, CERN fabricated the largest and most powerful particle collider in human history, the Large Hadron Collider, LHC, between 1998 and 2008. More than 10,000 researchers from over 100 countries assisted in this endeavor. The LHC sits within a 27 kilometers long tunnel on the border between France and Switzerland, about 175 meters underground. The very first crash recorded at the Large Hadron Collider had an energy of 3.5 tera-electron volts per beam, roughly 4 times that of the previous world record. The energy reached 6.5 tera-electron volts per beam once the LHC was further improved. Musk noted that the LHC excels at proton-proton collisions, and it can also accelerate lead-ion beams, conducting proton and lead impacts typically for 1 month. This is crucial for researchers testing various particle physics theories. The primary objective of the Large Hadron Collider is to test the properties of the Higgs boson and search for the vast array of new particles predicted by subatomic particle theories. Hadrons are composite subatomic particles made of quarks, held together by a strong force, much like how particles and atoms are held together by electromagnetic force. Protons and neutrons are well-known examples of hadrons. The LHC brings two colliding particle beams together so they can impact the Higgs boson, which is believed to be a fundamental particle associated with the Higgs field. It is the quantum excitation of this field, similar to how one might observe waves in the ocean. The boson resembles a new species in the particle zoo, lacking the quantum elements of fundamental matter and the carriers of quantum interactions like electromagnetic force, weak force, and atomic interactions. The Higgs boson was discovered at the Large Hadron Collider, a pivotal finding accomplished simultaneously by the two major experiments, ATLAS and CMS. It was reported on July 4, 2012, at CERN. At that time, the new scalar boson was found primarily in two rare decay channels, which provided the clearest signals, one decaying into 2 photons, requiring a completely quantum virtual process, and the other decaying into 2 Z bosons, the carrier of the neutral-weak interaction. The discovery of the Higgs boson confirmed the Standard Model of particle physics. Research into this elusive particle didn't end there. One of the significant findings since 2012 was the affirmation of Higgs boson properties. According to CERN, the investigation into this particle will expand during the LHC's third cycle, especially once the collider's high luminosity upgrade is completed in 2029. This will allow the LHC to conduct more collisions, giving researchers a greater opportunity to identify unexpected physics, such as phenomena that do not fit within the standard model. CERN estimates that when the collider is upgraded, it will produce 15 million Higgs bosons annually, compared to the 3 million produced in 2017. This could be crucial for identifying different types of Higgs bosons that go beyond the standard model of particle physics, with expectations of up to 5 distinct types of Higgs bosons, some of which might be produced less frequently than the standard Higgs. Even before these upgrades, researchers have produced compelling evidence for an exotic Higgs boson. But why does this matter? The Higgs boson and the Higgs field were incredibly significant in the early universe following its creation. They govern the very nature of the vacuum that exists in our spacetime, enabling matter and interactions to exist as we know them, including the emergence of mass in fundamental particles. Without the Higgs field and thus the Higgs boson, the universe would lack all atomic components, no stars, planets, or life. Why do you think the Higgs boson is known as the God particle? This moniker gained traction in popular media following its discovery. The term is often attributed to Nobel Prize-winning physicist Leon Lederman, who, out of frustration, referred to the Higgs boson as the goddamn particle because it was so difficult to detect. When Lederman wrote a book about the Higgs boson in the 1990s, he wanted to title it The Goddamn Particle, but publishers changed it to The God Particle, sparking a debate between science and religion that still concerns modern physicists. Regardless, the significance of the Higgs boson and the Higgs field cannot be overstated. Without them, fundamental particles would have no mass, implying that stars, planets, and people could not exist, which may help explain its lofty epithet. Beyond the evident need to describe this new particle, researchers continue to investigate the Higgs boson for two primary reasons. First, to understand how the physical vacuum in which we reside originated in the early universe, and second, to comprehend how this physical vacuum can be kept stable. The Higgs field is intriguing in that it imparts a non-zero mean expected potential energy to the vacuum. This is what fundamentally impacts our universe. Researchers believe that understanding the structure of this energy potential is essential for grasping the existence of electromagnetic force, which has infinite reach, and the weak force, which has a very limited range. To achieve this, scientists need to study how Higgs bosons interact with one another, necessitating the creation of pairs of Higgs bosons. The Higgs boson is central to the solution of the critical question of how all other fundamental particles acquire their mass. However, its mass is still not fully understood, as current theories do not adequately explain this mass and lead to potential instabilities. Quantum vacillations could upset the actual vacuum itself. Luckily, this is on timescales a lot greater than the Higgs boson's known life expectancy. Yet researchers are still looking for extra Higgs boson-like particles that would show the presence of new material science expected to balance out the Higgs boson mass. All of these contemplations support the investigation of considerably more information, and if practical access to greater collider energy is possible, this is why, 10 years later, many scientists throughout the world remain focused on the work. The Higgs boson was first proposed in 1964 and was discovered in 2012. Science aficionados have questioned why it took such a long time. This is because the Higgs boson is both huge and incredibly unstable. To make such a massive particle, researchers needed to concentrate a huge amount of energy in a small compartment. They required a high-energy collider. Once formed, Higgs particles decay in an assortment of ways, with only a small fraction discernible from the background. Researchers built the largest and most complex detectors to identify such particles, then they explored many billions of proton impacts to find a Higgs boson signature. Anyway, will CERN's ventures and discoveries enable us to make huge discoveries? Will it send us to our ultimate end? Scholars have three fundamental speculations about what CERN really depends on. The first and deadliest idea that has drawn some point fingers at CERN is that the organization is attempting to open a gateway to hell. Some believe that CERN's experiments with subatomic particles flying at the speed of light will propel humanity past the gates of the last fiery blaze. However, CERN has stated that the goal of creating antimatter is to better understand matter and mass. Wikipedia characterizes antimatter as subatomic particles having the inverse electrical charge of matter. Allies of the theory of how things came to be believe that antimatter was formed during the universe's inception and should be studied similarly to matter. Anyway, antimatter is quite unique. The second CERN intrigue speculation encompasses the Mandela effect. The Mandela effect is a phenomenon wherein numerous people remember an earlier event differently than it truly happened. Some conspiracy theorists believe that CERN's particle examinations will trigger disturbances in our world, driving our planet into another domain and resulting in a large-scale Mandela effect. Finally, some conspiracy theorists feel that human sacrifice occurs nearby at the CERN facility. A video supposedly released online in 2016 purportedly showed that ritual sacrifices take place at CERN. The recording showed hooded individuals walking around the CERN grounds, and it was thought that the tape depicted a girl being stabbed in the chest by the concealed individuals. According to The Guardian, a CERN representative stepped out to debunk the story, claiming that the ritual was staged as part of an elaborate joke. The question of whether a police investigation occurred afterward is yet to be settled. It is no surprise that CERN has long been the focal point of conspiracy theories. Consequently, it's to be expected that on July 5, 2022, when researchers began operations following 3 years of upgrades and maintenance, conspiracy theories would arise online. While scientific enthusiasts might be frustrated with these disclosures, it is evident that CERN has no desires to construct a doorway to damnation, the future, or any other aspect. Phantom particles detected from proton beams continue to zip around the 27-kilometer circle of the world's greatest atom smasher, which is situated more than 300 feet underground. For nearly a decade, its ability to smash particles together at exceptionally high energies has allowed humanity to see into the obscure frontiers of physics. The LHC's Forward Search Analyze indicator has produced a startling result. For the first time, it identified high-energy neutrinos produced by a particle collider, detecting 153 neutrino interactions with remarkable precision. This massive achievement in particle physics could assist researchers in better understanding the universe's intensely complex neutrino interactions, as well as revealing the mysteries of how stars consume and explode into supernovae. Neutrinos are tiny subatomic particles that exist essentially everywhere. They are produced when atomic nuclei emerge or split apart, formed by large beams, radioactive decay in Earth's particle accelerators and nuclear reactors, as well as the natural radioactivity of potassium and bananas. Anyway, these massless and chargeless particles represent the ultimate phantom. Once produced, they rarely interact with matter. Remarkably, around 100 billion neutrinos travel through each square centimeter of our bodies, but they are so elusive that we can't feel them. This mysterious characteristic has given them the nickname phantom particles, and researchers have been hunting them since 1956 when they were first detected hurling from a nuclear reactor. Physicists found evidence of 6 neutrinos in 2021, but it took them 2 years to gather sufficient proof to demonstrate that these ethereal particles were authentic, as verified by James Boyd, a particle physicist at CERN and co-representative for Fair Ghost Particles. These phantom particles can show us deep space in ways that other methods cannot. These very high-energy neutrinos at the LHC are crucial for understanding engaging particle astronomy discoveries. The endeavor will collect data until the end of 2025. Researchers expect to find more of these phantom neutrinos and unveil the physics secrets that we have yet to explore. Scientists are waiting with bated breath to see what CERN will reveal next and what the upcoming discoveries will mean for the future of science.